Okay, so shall we continue? Here we are again. I can't yet see my slides. Okay. So yeah, thank you. I think this is where we stopped, and then I said I will introduce logistic regression as a particular example of doing maximum likelihood estimation. I will skip that part. I shortened the slides a little bit to adapt to the speed of the presentation this morning. Instead, I will just show you another example without going into much technical detail here, which is the example of neural networks, which was already mentioned a couple of times this morning. And I have the feeling that many of you are interested in neural networks and things such as deep learning. And also neural networks, in a sense, can be seen as doing maximum likelihood estimation. Why? So neural networks, that was already mentioned this morning, are parameterized models. The set of parameters here corresponds to the weights you put on the edges. Yeah? In the simplest case, this is in the case of a simple feed-forward neural network here, for example. And this is our parameter vector, theta. Then what many neural networks do is in, for example, the case of binary classification. Suppose we have a binary classification task, distinguishing people or whatever, producing probability or pseudo probability in the end by putting a transformation, a suitable transformation in the last layer. So here, this last neuron here, you can imagine takes gets some inputs. These inputs are weighted and summed up to obtain such a score S, and this score is then transformed or mapped into the unit interval by applying such a sigmoidal shaped transformation here. So you end up with a prediction, which is a number in the unit interval, and which you can interpret if you want as a probability. And what you want, of course, is that if the example input here is a positive case, you want a probability close to 1. If it's a negative case, you want a probability close to 0. And now the question is, how can you train the neural network? How can you learn suitable parameter values, weights for the edges? And to do this, we can invoke this principle of maximum likelihood. Yeah? Maximizing the likelihood here means maximizing the product of probabilities of the truly observed class given the prediction. And the prediction is what is produced here via this parameter vector theta. And as I said this morning, maximizing this likelihood is equivalent to maximizing the log of the likelihood, which is given by the sum of the logs of these probabilities. And in this way, you can train your neural network. Interestingly, if you look at this closely, this is a sum of penalties for predictions. This should remind you of what we introduced this morning as empirical risk minimization. And indeed, maximum likelihood estimation in this way is equivalent to doing empirical risk minimization with a specific loss function, namely the logistic loss or cross-entropy error, which is defined in this way. Yeah, you take as an input a score, which is a real number on a real number, can be positive, negative, and an observed class, which is 0 or 1. And you see, this is just here, this is a transformation of the score into a probability. And you see that the loss goes to 0 if either the class is negative, so the y is 0, and the score goes to minus infinity, or the class is positive and the score goes to infinity. So if you have a positive example, you want to predict high scores. If you have a negative example, you want to predict low scores. Yeah, so this is an example, if you want, an example of maximum likelihood estimation. And this brings me to the next topic. I want to briefly speak about so-called proper scoring rules. This log loss, this cross-entropy error I just showed on the previous slide, is an example of what is called proper scoring rule in the literature, in the statistical literature, many machine learning people are not so much aware of these proper scoring rules, although they are very important. This is why I want to mention them here, and also because they establish a nice connection between different parts of my tutorial. They directly relate to calibration, which is something I said I will mention briefly, and Melis is going to speak about this in more depth on Wednesday. And they also relate to my presentation about this epistemic uncertainty part. So this is why I would like to mention these proper scoring rules. This log loss or cross entropy loss, or let's say this maximum likelihood approach, is not only a well-established and theoretically sound way of learning, it is also a good way of learning if you want to predict accurate probabilities. So there is a direct connection to probability estimation, and this can be established via this notion of proper scoring rule. So if you consider a probabilistic prediction for any input query X over a set of, let's say, K categorical outcomes, so we are in a K-class classification scenario, then the prediction comes in the form of such a probability vector with K entries, summing up to 1. So it's an element of the K simplex. The true distribution conditioned on X, the true distribution on outcomes conditioned on X, is also such a probability vector, the ground truth vector, let's say. And we can consider the observed class as a random variable which is drawn according to this distribution. So which is a random variable with a multinomial distribution. Yeah. We can also encode, if we want, we can use a dummy encoding of the outcome, the realization of this random variable in terms of a vector, again of length k, where we put a 1 at the position of the class that occurred, and zeros for all other entries. So then, expressed in terms of this predicted probability, the log loss can also be written in this form here. It's a loss function that takes the predicted probability vector as input and the observed class and returns as a penalty minus log the probability assigned to the class that has been observed. So what is now a proper scoring rule? We call a loss function L a proper scoring rule if the expected loss minimizer exactly coincides with a true probability vector P. So that means if we look at the expected loss of a prediction P hat and an outcome of our random variable Y, the observed class, and we take the expectation with respect to the true distribution, which the learner, of course, doesn't know, but which we assume to exist, the true distribution of the classes, the K categories. And we minimize this expression here, then the true P, the true probability, is exactly the minimizer of that expected loss. In other words, if our learner is doing expected loss minimization, what it will do is predicting, or what it should do is predicting exactly the ground truth probability distribution P. So in other words, such a proper scoring rule gives a strong incentive for the learner to predict correct probabilities, to predict the ground truth probabilities. A scoring rule is, we call a scoring rule a strictly proper if this minimizer is even unique. Yeah? If it's not only, if the true P is not only one minimizer of that expectation, but if it's the minimizer of that expectation. So yeah, this I said already. This means that given a query X, a learner which is penalized by such a strictly proper scoring rule has a strong incentive to predict the true conditional probability of the outcome given X. So in a sense, we can say that using a strictly proper scoring rule as a loss function is exactly the right thing to do if you want to do good probability prediction. Yeah. One example of such a strictly proper scoring rule we have already seen. I said the log loss is such an example. Another example is the Breyer score, which is the sum of the squared differences between the predicted probabilities and this encoding of the observed class. Remember, in this encoding, one of the entries is 1 and all the other entries are 0. Yeah? For the k of the observed class, the entry is 1, all the other entries are 0. And this you can see by some simple calculations. Here on the left-hand side, you see the expected loss. So this is the loss if the kth class occurs. This is the probability that the kth class occurs as an observation. You take the expectation, so the weighted sum, you rearrange a little bit, and then you end up with this term here. And this is exactly minimized by taking p hat k equal to pk for all k. So exactly estimating the correct probabilities. So I just want to say one more thing about these proper scoring rules. We can extend, so to say, these proper scoring rules to a scoring function which compares two probability distributions with each other. Predicted one, p hat, and a ground truth one, p. Yeah? By defining this as the expectation of this expression s p hat y, namely the, let's say, expected loss, where the expected loss for predicting p hat, where the expectation is again taken with respect to the ground truth distribution. And there is a direct connection to between these proper scoring rules and so-called divergences, because we can, given this definition of a scoring function, we can define a divergence measure, a measure that tells us how far apart two probability distributions are from each other, in this way, yeah? S of p hat p minus SPP. Yeah? And one can show that this divergence is a real divergence, namely it's non-negative, and if and only if this loss function is actually strictly proper. And even separating, this means that the divergence is 0 if and only if p hat is equal to p. The second term here, this S of pp, is also called an entropy. Yeah? And a classical example, again, take the log loss. For the log loss, the divergence that you obtain, if you use this definition, is the famous KL divergence between probability distributions. I'm sure you all heard about already. And the entropy is just the not less famous Shannon entropy. Yeah? So it's an interesting special case again. And for the Breyer score, we obtain as a divergence just the Euclidean distance between the two probability vectors. And as an entropy, we obtain the so-called Gini index, which many of you will also know, especially people maybe with an economics background. It's a quantity that is also often used in economics. Just as a side remark, the 0-1 loss, which we also discussed this morning, is a proper loss, but not a strictly proper loss. So it's not exactly the right loss to use when you want to do good probability estimation. Okay, given this definition of a divergence, I just wanted to mention one more thing, namely that we can decompose the expected loss for a proper scoring rule, taking the expectation again with respect to the ground truth distribution, into two parts. So there is this additive decomposition of the expected loss, namely in terms of this divergence and this entropy. And this is not uninteresting with respect to what I will speak about tomorrow, this distinction between aleatoric and epistemic uncertainty. This part here, this entropy, in a sense you can interpret as the part of the loss that the learner cannot avoid. This is only a property of the ground truth probability, P, not of the prediction P hat, only the probability P. And it's clear that the more, let's say, random the probability distribution, for example, the more uniform the distribution, the harder it will be for the learner to guess the right class, to predict the right class. So there is a certain loss that the learner cannot avoid at all, depending on how uniform, let's say, this distribution is, on how random the outcome is. This part here, this is something that the learner can work on. And this is exactly related to what I called approximation error this morning, what the learner should try to do in order to minimize a scoring rule in expectation is to make a prediction P hat that is as close to P as possible. Yeah? And again, you see that this is the right incentive for a learner to do good probability predictions. Okay. So this brings me to the last sub-part of this second section. And again, I will be a bit shorter than originally planned to have more time for the rest. The Bayesian paradigm to machine learning is, of course, also very important to mention when speaking about uncertainty in machine learning. And what do we mean actually by Bayesian machine learning? Essentially, we mean applying this Bayesian paradigm of statistical inference to problems within the realm of machine learning. And what does that basically mean? It means that we are doing learning essentially by applying the famous Bayes rule. Yeah? In the case of machine learning, turning a prior distribution over the hypothesis space. So the Bayesian approach would start with formalizing prior belief about which hypothesis might be the true one, yeah? Putting a probability distribution over the hypothesis space, over the set of all possible models, and then in the light of observed data, updating this belief by turning the prior distribution into the posterior distribution. And I guess you all know how that works. Yeah, by applying Bayes' rule, the posterior probability of a hypothesis given the data is proportional to the prior times the likelihood, times the likelihood of the hypothesis, namely the probability of the data given the hypothesis. So this approach is especially, of course, interesting also from an uncertainty representation point of view. Why? Because the learner, a Bayesian learner, a proper Bayesian learner, will not just pick any of the hypotheses and say, okay, that's it, this is the model you should take for making predictions. It will always maintain a complete distribution over the entire hypothesis space. And the more peaked that distribution is, the more certain or the less uncertain the Bayesian learner actually is. So imagine you have such a posterior distribution over the hypothesis space, then how can you make a prediction for a new query input xq, yeah, for which you want to predict a class? The proper way of doing that in the Bayesian approach is to do what is called model averaging. You look at all the predictions that are made by all the different models H in your hypothesis space. So what is the prediction of your model H for the query instance XQ? And then you weigh this according to the posterior probability of that model. Yeah? So you basically compute this integral. You integrate the predictions with respect to the conditional or the posterior probability over the hypothesis space. This is called model averaging because you average the predictions of all the different models. You can imagine that this is very costly. You have to compute an integral over potentially very complicated hypothesis space. Sometimes it's even not possible. Imagine your hypothesis space is the space of neural networks or so. And therefore, Bayesian inference in this proper way often cannot be done or is intractable. Therefore, people have worked a lot on approximate methods. So methods that somehow approximate this inference step, turning a prior into a posterior and then doing model averaging for prediction. This is also related to ensemble methods. You can consider an ensemble of methods as a kind of discrete approximation of this posterior distribution. One alternative to reduce complexity is to go for just one single model, not doing this averaging over all models, but just picking one of them, presumably the one which has the highest posterior probability, the maximum a posteriori probability model, and this is called map inference if you do this. But then, of course, you again lose at that point information about how certain or uncertain your learner is about this particular model H. So there are a few exceptions for which Bayesian inference becomes tractable, and you can do this updating and this inference in an analytical way. So no need for approximations of which you never know how good they are, and so on. And one important case is Gaussian processes, which I wanted to mention briefly here. And doing learning and inference with Gaussian processes becomes tractable due to the nice properties that Gaussians have, normal distributions, yeah, multivariate normal distributions. Normal distributions, as you may know, have many nice properties. You can add up two distributions and they are, what you produce is again a normally distributed random variable. You can condition a Gaussian distribution and you obtain again a Gaussian distribution. You can marginalize and the marginal of a Gaussian distribution is again a Gaussian and so on. So you can do many operations without leaving the class of Gaussian distributions. And this is a nice thing to do. So Gaussian processes, as I said, I modified my slides, removed basically all technical things. So just very briefly showing you some pictures. I wanted to mention them here because Gaussian processes is one important way of doing learning with the representation of uncertainty, with a proper representation of uncertainty. So Gaussian processes you can think of as extensions of multivariate Gaussian distributions to an infinite-sized collection of real-valued random variable. More specifically, they can be thought of as distributions not just over random vectors, but over complete random functions. Yeah. So imagine you have an input space X, for example, here X equal to two-dimensional Euclidean space, and you generate a random function over this space. This is what we are interested in. Gaussian processes define a specific type of a stochastic process, so a collection of random variables f of x, which are indexed by such an index set x, which in our case is the instance space, our instance space. And the property that makes such a stochastic process a Gaussian process is that if we condition on regardless of what subset of that space, so for example, if you take 3 of the instances, x1, x2, x3, and we look at their joint distribution, which is a marginal of this high dimensional or infinite sized distribution over random functions, then this marginal is always a Gaussian, yeah, So the distribution is a joint distribution with a mean vector, mu1, mu2, mu3, and a covariance matrix. And the covariance matrix establishes the connection between the outcomes at these 3 points, f of x1, f of x2, f of x3, that we observe. They are not just drawn randomly and independently of each other. They are connected via this covariance structure. And the stronger the covariance between them, the more, let's say, regular the function is that you generate at random. Yeah, so this is a nice property. This is very connected, by the way, to methods in the geosciences, for example, applied a lot, which is called kriging. Maybe some of you heard about very similar ideas actually there. Here is a one-dimensional illustration. So imagine our instance space is just one-dimensional. We have 2 points, x1 and x2, and our assumption is that if we draw random values at these 2 points, they are both Gaussian. Yeah, this is supposed to be a Gaussian distribution with a certain mean, mx1, mx2, and the 2 values have a covariance structure. So they are not drawn independently of each other, but if you look at their joint distribution here in this 2-dimensional space, then it's a Gaussian with a certain covariance structure. Yeah. So more specifically, how is such a Gaussian process described? It's characterized by what we call a mean function. This is this m I already mentioned on the previous slide. M of x is the expected value at the point x, and by a so-called kernel function, k, or covariance function, which defines us for any finite collection of instances this covariance matrix, yeah, that we need, a covariance structure. Yeah? So k of xi, xj is telling you something about how much these 2 points interact with each other. Good. Then, given this assumption, what we can do by applying the standard Bayesian approach of learning and doing inference is the following. Suppose you are given a set of observations, these red points. So we have an observation at point x1, we have an observation at point x2 and x3, and now you want to predict for x1 prime and x2 prime. Suppose you want to make predictions there. And then we can do standard Bayesian inference, yeah, condition on the information that we have seen, basically looking at the joint distribution at all these points, which we know is Gaussian by assumption. And then a condition on x1 prime, x2 prime to come up with predictions at these points. Yeah? So as I said, I skipped the technical part, which is not very difficult, but it's a lot of formulas and so on. And in this way, what you will produce is a prediction of a Gaussian here at x1 prime and a prediction of a Gaussian here. And the nice thing is now, again, coming back to this problem of proper uncertainty representation, we do not just get a point estimate, a single estimate for the outcome, y1 prime and y2 prime, but we get a distribution. And the distribution is telling us something about how certain or uncertain the learner actually is about the distribution it makes. So it looks like this if we, for example, if we produce such a prediction not only for 2 points, but for basically all points here on the line, we obtain Gaussians around a mean function that we estimate, this blue one here. The red points are the points that we have observed, and distributions around, and the distributions are characterized here by this confidence band. And you see that the wider the band here, the wider the confidence band, the less certain, this confidence band, by the way, is the 95% confidence region, so an interval that covers 95% of the probability mass. The wider this interval here, around a point prediction, the less certain the learner is about this prediction. And you also see that the more data points you have observed in a certain region, the more narrow this confidence band becomes. And the more data you have observed, if we increase the number of observations, it becomes more narrow and narrow. And in this way, you have a good idea of how certain or uncertain actually your predictions are. So this is a meaningful way of doing prediction. This is in the case of regression, of course. You can also do Gaussian processes for classification. Then you do a similar thing as we discussed before. You put a nonlinear transformation on top, yeah, turning these real valued predictions into probabilities, for example. Then, however, the inference again becomes more tricky, because then these distributions are no longer Gaussian, and you have again to refer to approximate inference techniques here. Okay, so nevertheless, these Gaussians or these Gaussian processes is a method that is certainly important from an uncertainty representation point of view, and goes into quite good direction here. So briefly, I want to say a few words about calibration, as I said before. To motivate this, let me mention that learning good probabilistic predictors, despite having these ideas of proper scoring rules and probabilistic models, maximum likelihood, Bayesian learning, and so on, which in theory at least should produce good probability predictions, remains quite a challenge, especially for classification, when you want to predict probability distributions over categorical outcomes. Many methods, like we had this example of decision trees this morning, but also if you train support vector machines and do Platt scaling, which by the way is already some sort of calibration, or you do neural networks with softmax and so on, produce scores which are good enough to make good classifications. So if you have to decide for one of the classes, take a discrete decision, then this decision is often correct, but they do not really qualify as accurate probability estimates. And even such methods like logistic regression and Gaussian processes and so on do often not produce very accurate probability estimates. Yeah? Although they should do actually in practice, and the reasons for that are manifold. I don't want to go into that much detail here. Yeah, the same remark, of course, for methods such as naive Bayes and so on, which also produce probabilities as predictions, but due to the strong assumptions in the case of naive Bayes conditional independence, these are again predictions that are often very biased, let's say. And calibration tries to do something against that. Yeah, there is a question, yeah. The mic. It's over there.
Actually, a very short question. So why especially about the classification? Why is it not the case, for example, for regression? Because one would think that the lower the dimensionality in case of, for example, classification should be, relatively speaking, easier the task of getting more results.
Yeah, okay. Yeah, it's a good question. I also don't want to claim that this is perfectly true in general, but the thing is that if you train models for classification, you often have, like in the case of Gaussian processes, for example, some sort of nonlinear transformation in between. You learn a kind of latent regression function and then turn it into a discrete or categorical representation of probabilities, which makes things a little bit harder. There is one more assumption of distributional assumption you have to make at this point. But it's perfectly true, of course, that regression or estimating probability distributions in the case of regression is not an easy task either. I certainly didn't want to say this, especially because in regression, what you typically have to make also is distributional assumptions. Gaussian processes, in a sense, are relatively flexible in that regard because they at least don't make strong assumptions regarding the global relationship, but still they have this assumption of Gaussian distributions. Of course, that is also not perfectly true either. Still, they work actually quite well in the case of regression. So specifically for Gaussian processes, they tend to work better for regression than for classification. But I don't want to overgeneralize this. It's certainly a good question. I don't know exactly, maybe someone has more experience with this specific comparison, but at least what is true is that for classification, it remains a challenge. Okay, so yeah, so what many machine learning methods actually deliver, again, in the case of classification, or even now, let's look, let's look still at the case of multivariate classification. So we have k possible categorical outcomes, is scores S1 to Sk, which are telling us something about how likely or unlikely the different categories are, but which do not really qualify as proper probabilities. In support vector machines, for example, some distance to the hyperplane or so. These are meaningful scores in a sense, which you can compare with each other, but they are not really good probabilities. Other methods do not only produce scores, but something that is already a bit closer to probabilities, namely scores in the unit interval, which even may sum up to 1. So at least they look like probabilities, but still they might not be really good probabilities in the sense of guaranteeing an accurate approximation of the ground truth probabilities. They are more something like pseudo probabilities. Yeah? They are not well calibrated. However, calibration is really important and a prerequisite for many downstream tasks, so to say, for decision making, for coming up with a recommendation, a prediction, a prescription, or whatever. So for from the perspective of uncertainty awareness, these are very important and desirable to have. So it's the question whether we can't perhaps improve these scores or pseudo probabilities that are coming from a machine learning method and turn them into well-calibrated probabilities. I gave you this example already in the morning where you extract probability estimates from a decision tree. And we said that these are likely to be biased more towards the extremes. And the question is, what can you do about this? And here is where calibration comes into play. Calibration is actually the idea of taking these scores or pseudo probabilities and somehow improving them by adding another mapping as a post-processing step, by mapping scores to hopefully well-calibrated probabilities. And I will skip this part mostly, again, referring to Melis tomorrow. I just show you one picture here where what is plotted is the predicted probability, is the true probability versus the predicted probability. And you see here such typical examples of a biased prediction. So here, for instance, you see an example where on the left we have a bias toward 1/2. So this learner here, this predictor, has a bias toward predictions of 1/2. So here this probabilities where the true probability is actually 0.25, the predicted probability is 1/2 or close to 1/2, and the same here. So this is a learner which has a tendency to say, I don't know, it's probably somewhere in the middle. And this learner here has a tendency has a systematic underestimation of the predicted probability, for example, of the true class. And then the question is, what can you do about it? And how can you maybe repair these pseudo probabilities and turn them into better calibrated probabilities? Here you see the same in terms of what is called the reliability diagram, where you group predicted probabilities into subgroups here by defining such by defining a partition on the unit interval. And if, for example, you group all the probabilities, predicted probabilities between, let's say, 0.5 and 0.75, then what do you expect in terms of the real proportion of positives you observe within that class? It's, of course, a value between 0.5 and 0.75, 0.625 or something like this. So something close to the diagonal if you look at this histogram here. And any deviation from this diagonal will tell you that your estimates are somehow biased. And then you can think about how to repair them. Good. So Melis will speak about this in more detail tomorrow, so I will skip the rest of this presentation here. And move on to the fourth part of my presentation, which is about making set-valued predictions, especially with this approach of conformal prediction that I already mentioned very briefly this morning. So what is conformal prediction? I just noticed that the references, obviously I didn't BibTech again, my presentation after the update, but in the original you find the references. Sorry for that. So conformal prediction is actually a framework of, let's say, reliable prediction that is rooted in classical frequentist statistics and especially hypothesis testing. So in a sense, it's quite orthogonal to Bayesian learning and Bayesian inference. So it's, yeah, as I said, rooted in frequentist statistics and makes use of hypothesis testing. Why is conformal prediction interesting from an uncertainty representation point of view? It's because conformal prediction does not deliver just point estimates, but delivers set-valued predictions, which are guaranteed to cover the true outcome with a high probability. And as a user, you can even control this probability with which conformal prediction makes a correct set-valued prediction. So, for example, if you want to predict for handwritten digits taken as an input, an image taken as an input showing a handwritten digit, what is actually the digit that is represented there? Conformal prediction will not just guess one of the digits, one of the 10 digits as an outcome. It will not deliver a probability distribution over the 10 possible outcomes either, which is something that a probabilistic learner would do, but it does something different, and this is another way of representing uncertainty, of course. It delivers a set. This is what I mean by set-valued prediction. So for this image here, as an input, for example, it will say, oh, I'm not sure actually what that is, but it's with high probability, with a probability of at least 90%, it's either a 2 or a 3 or a 9. This is the type of prediction that conformal prediction will deliver. And it does so not just in a heuristic way, but with a theoretical guarantee that I will explain a bit more on the next slides. So how does conformal prediction work? So imagine that we are given, as observations so far, a sequence of data points. Originally, conformal prediction has been developed in an online setting doing transductive inference. And then later, I will come to this, an inductive variant of conformal prediction has also been developed in order to reduce the computational burden of the approach. But let's look at the more original setting of conformal prediction. So you have seen a sequence of data, like for example, handwritten digit x1 and the digit that was represented, handwritten digit x2 and the digit that was represented, and so on. And now you are given a next one, xn plus capital N plus 1, and you have to make a prediction. The dot here means you don't know what, for example, digit is represented here. You want to predict it. Now, very high level, on a very abstract level, what conformal prediction is now doing to come up with this prediction region or prediction set I was mentioning before is to hypothetically plug in every possible candidate outcome here for the dot, and then testing the hypothesis that this might be the true outcome. It's doing hypothesis testing at this point, classical statistical hypothesis testing. So it's testing whether this is a plausible candidate, so to say, the Y. It plugs in there, for example, the digit 0, the digit 1, the digit 2, and so on. And then it looks, so to say, at the data and checks how regular or irregular the data looks like, or how strange, so to say, this example xn plus 1 y looks in the light of the other data that you have observed. And if it looks very strange, if it looks strange enough, then it rejects this hypothesis, and then the y is not included in your prediction set. But if you cannot reject this hypothesis that the outcome here is the y, then the y is included in your prediction set. That is the basic idea. Yeah. So yeah, this is what I just said. Only those outcomes for which conformal prediction cannot reject this hypothesis, the null hypothesis that the outcome is y, those are not included, and all the others are included in the prediction set. So I said what the basic idea is to somehow quantify or base this decision of whether to include or exclude a candidate outcome y in terms of a degree of strangeness. How strange does this example actually look like? And formally, this notion of strangeness is captured in terms of what is called a nonconformity score. So we would somehow like to measure how much a hypothetical data point xn plus 1 y conforms or does not conform to the data that we have already seen so far, the first capital N data points that the learner has already seen. And then hypothesis testing is done in a non-parametric way, as you will see in a minute. So a nonconformity function formally is a function that takes a data pair as an input, an x and a y, and returns a real number as an outcome, with the idea that the higher the value, the less conform this data point actually is. So smaller numbers are say indicating that the example is conforming to the data you have seen so far, and higher numbers that this example doesn't conform. Yeah, so let's call these values alpha. Alpha is the nonconformity score, that is assigned to such an input-output tuple xy. Okay, this is what I said already. So here is an example, just as an intuition. Suppose a very simple situation, very extreme now, of course, it's not always as clear as this, but a simple example. Suppose that we have seen some positive examples and some negative examples. And now we want to make a prediction for this point here, this gray shaded region. So yeah, this point here. We test, or what conformal prediction would do is to test both classes as hypotheses. So let us hypothesize that the class here, the class label of this example is black. Then we obtain this data set. We enrich the data that we have seen by this additional hypothetical example, and this looks completely normal. So you will say, okay, this looks quite plausible. Nothing speaks against this hypothesis that the class is black. When we hypothetically put a positive example here, so we hypothetically label this instance positive, then this looks strange, right? Even visually, if you look at it, you have all, let's say, black examples around, and then here one single cross, so this looks really a bit strange. So intuitively, you would reject this hypothesis that the class label of this instance is positive. So this is the basic idea. And of course, you cannot just apply it to classification. You can also apply it to any other prediction task, including, of course, regression. So imagine we have seen the green points as examples so far. And then you have to make a prediction here at the position of the dotted line. Yeah. Then if you hypothetically take any value here, for example, this red one or this red one or this red one, they all look quite plausible, you would say, because if you enrich your data set by these data points, then this still looks like a reasonable data set. But if you put, for example, hypothetically the outcome here, or if you put it here, then this data set suddenly looks a bit strange, yeah, because you have this irregularity. And again, you would probably reject the null hypothesis then for these data points. And if you do that for every possible candidate outcome, which in the case of regression, of course, is an infinite number of real numbers, what will you probably come up with? How will the prediction region then look like if we produce this prediction region here at this data point? What will it most probably look like? What will it be? What kind of set will it probably be? A line, yes, but what kind of line? A bit more. A line is already good because the set will most probably be convex, yeah? It probably will not be a set that has holes in the middle. It will be an interval, yeah? Maybe you meant this, I don't know who said that line. Okay, an interval, yeah? It will probably be an interval in this region here. The question is only how wide should that interval be, but you will certainly exclude these extreme points here and include those close to the data points you have already seen in that region. No, wrong direction. Okay, so here is another example of or let's say a concrete example of a non-conformity function. Suppose we have, in this case, it's a 3-class classification problem. We have classes red, green, and blue. And we do nearest neighbor classification, or we define the nonconformity function in terms of nearest neighbor information, which is just one example of defining a nonconformity score, but maybe not the worst. So what is the idea? The idea is the following. We have a point for which we want to predict, this point here. We want to predict whether the class is red, green, or blue. We hypothetically put every color here. So we hypothetically, for example, put red for this point. And then we measure the nonconformity in the following way. We look at the K, data points from the same class that we hypothetically put there and sum up their distances. And we look at the K examples in our data set from a different class, so for example, not red, and again sum up their differences. So this means that this score here will be the lower, the more examples from the same class you have in the close proximity. Yeah? If the score gets very high, it means those examples from the same class are far away, whereas the others are closer. And this is somehow speaking against this class. So the lower the score, the more this hypothetical class label conforms to the data in a nearest neighbor sense. Okay, so recall this sequence of data that we introduced in the beginning. Suppose we have seen capital N data points so far, and we have an N plus first data point for which we want to predict. For all these data points, if we hypothetically put in a candidate outcome here for the N plus first instance, then we have capital N plus 1 data points. For every data point, we can compute the nonconformity score given our nonconformity function, which of course we need at this point. Yeah? So we obtain a sequence of alphas here, the alpha 1 to alpha N plus 1 nonconformity scores. These nonconformity scores we can sort in increasing order. Yeah? Sigma here is a permutation that sorts the N plus 1 data points in such a way that the one with the lowest nonconformity, so the highest conformity, the less strange data point, so to say, comes on the left, then the next one, and so on, and the N plus first here on the right hand side, this is the most strange one, which has the highest degree of nonconformity. Now, why is that meaningful information, this sorted sequence here? It's meaningful information because under the assumption, remember this idea of hypothesis testing, under the assumption that our hypothetical choice of the outcome here, yn plus 1, the hypothetical outcome for the n plus first data point, is in agreement with the underlying data generating process. So it has been generated by the same process as the other n data points that are real data points that we have seen. And here comes one important technical assumption. This data generating process is exchangeable. It has an exchangeability property. More on this in a minute. It's not a very strong assumption, actually. Then every permutation sigma has the same probability of occurrence. Yeah. So every permutation, whether, for example, the fifth data point is the most conforming, and then the third, and so on and so on. This is the same, should have the same probability as the second has the highest conformity, and then the 10th one, and so on and so on. So every permutation should have the same probability. And what does that mean? Actually, what does that mean? In which case now should, or what are the cases in which we should have a tendency to reject this candidate outcome yn plus 1 as a plausible candidate? Under this assumption that it's really a data point that has been generated by our process, for this alpha n plus 1, any position has the same probability to occur. Any position has the same probability to occur, right? So if our alpha n plus 1 occurs here on the right-hand side, so it's one of the most non-conforming data points, this is the case where we should become skeptical, yeah? Because it has the same probability to occur everywhere, but the non-conformity is somehow surprisingly large. Surprisingly large. You have a question, Melis?
I could ask now as well. So just maybe you're just getting to that. Is exchangeability then just kind of a more general than IID assumption? You're probably getting to that.
Exactly. So exchangeability, exchangeability is an assumption that is weaker actually than IID. So if your data is IID, then it's exchangeable. If it's exchangeable, it's not necessarily IID. What we mean by exchangeability is the following. A finite sequence of random variables x1 to xn is exchangeable if the joint distribution of these capital N random variables remains unchanged under any permutation. So you can permute these random variables, these capital N random variables, and the joint distribution won't change. So the distribution of this vector here, x sigma 1 to x sigma n, is the same as of the original vector x1 to xn. This means that the cumulative distribution function here, this cumulative distribution function of the random variables is basically, it means this, that this function is symmetric in its arguments. And as I said, it's weaker than IID. You can construct examples where you have a sequence of random variables that are exchangeable but that are not IID, but not the other way around. So it's a weaker assumption. It's not a very strong assumption to make. This is yeah, what I wanted to say. So it's a relatively weak assumption. Okay, so this is what I just said here. The probability that our alpha n plus 1 is among the epsilon % highest nonconformity scores in our sequence is relatively low. It's at most epsilon, yeah, under this assumption that it's really generated by our data. And this notion can be captured more formally in terms of p-values that we can associate with every candidate. Again, this notion of a p-value you will be quite familiar with. It's an important concept of classical statistics. We can associate a p-value with every candidate outcome y, and this p-value is defined in terms of the number of data points among these n plus 1 for which the alpha is at least as large as alpha n plus 1 divided by n plus 1. So it's the percentage of other data points that are more strange or at least as strange as our hypothetical data point xn plus 1, yn plus 1. And it's clear that the lower that value, the less plausible it is that this outcome is a real outcome, because there are hardly any more strange data points in your really in the data that you have really observed. Yeah. So according to what we said, the probability that this p-value here is lower than some epsilon is upper bounded by epsilon itself. It's upper bounded by epsilon itself. Yeah, so, and this is the basis for doing this hypothesis testing, namely the hypothesis that the real outcome, alpha n plus 1, is given by some specific hypothetical y, can then be rejected for those candidates for which this p-value is lower than some predefined value of epsilon. And the probability that we make a mistake by that decision here, by rejecting the null hypothesis, is then controlled by epsilon. It's at most epsilon. Yeah. So it means that by construction, this set-valued prediction that we produce is guaranteed to cover the true outcome with a pre-specified probability of 1 minus epsilon. For example, 95% or so, if we take the epsilon equal to 5%, 0.05. Yeah.
There are no problem of multiple testing here because we're testing for multiple classes.
Yeah, it looks like this maybe at first sight. Yeah, but it's indeed it's covered, let's say, by the way the prediction set is constructed. Yeah. So it's theoretically. So I think I also have oh, it's again. I always. Do I go in the right or wrong direction? I think I have the more formal result on one of the next slides, where this guarantee that is given by conformal prediction is specified in a slightly more formal way. I mean, this guarantee simply holds for every candidate outcome, including the one which is the real outcome. And for this real outcome, you have this error probability, and therefore, the probability that it's incorrectly rejected is given by this, it's upper bounded by this quantity epsilon. One other important remark here is that these error bounds are valid by construction of this prediction region or prediction set, regardless of the underlying nonconformity function. This is important. So it doesn't matter actually what nonconformity function you take. You could in principle even take a random function. Yeah. However, the nonconformity function has an important influence on what is called the efficiency of the predictions, and by efficiency we mean the size of the prediction region. If you take a good nonconformity function, your prediction sets will not only be valid in the sense of covering the true outcome with high probability, they will also be informative, namely small. If your nonconformity function is not a good choice, is not a good nonconformity function, your prediction regions will still be valid, but they will not be very informative because they become very large. So for example, in the case of a digit prediction, it won't help you very much if the conformal predictor says this is either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Yeah, I can guarantee. Sure, it can guarantee, yeah, but it's not a very informative prediction to make. As I said before, I have till 5:30, right? Okay, so this fits, I think, quite well. So as I said before, this original version of conformal prediction has been developed in a transductive setting. Transductive meaning that you tailor your prediction specifically to the query input xn plus 1. Yeah? And for every query input xn plus 1, you have to redo this whole process. If your nonconformity function, for example, also involves fitting a model to the first n data points you have seen so far, you also need to refit that model every time. This is, of course, computationally expensive. And this is why people also thought about inductive variants of conformal prediction, which are computationally less costly and which avoid that you have to refit a model in every iteration, every time. So inductive conformal prediction, therefore, is an alternative that is computationally less expensive, ICP, And there are different ways in which you can do that. What is nowadays commonly used is what is called split conformal prediction. ICP is then realized by splitting the by splitting the training data D into two parts. One which is the proper training set. So suppose we have n data points seen. So far, this is our training data. We take away capital M for what we call calibration. This is our calibration data. And the rest we use for training. So DT is for training, and these capital M remaining data points are for calibration, for basically computing the distribution of these alphas, of these non-conformity scores. So how does it work? Imagine, for example, this is only an example, but it's often done like this, that we compute non-conformity scores by fitting a probabilistic classifier, H, on our training data. And then we define the non-conformity of a data point xy in terms of 1 minus the probability that is assigned to the outcome y. This is a meaningful non-conformity score because the higher the probability that is assigned to y by our model, the lower the degree of non-conformity. P here is the probability that is assigned to the outcome y by our model X. If we fit a model, for example, which does digit classification, and we have an input image, and the probability of 7 is 0.9 predicted by the model, then this looks like a quite conforming candidate outcome. If the probability is only 0.1, then this is highly non-conforming. So then we train such a model on the training data, and then we can apply it to the calibration data. For every data point in the calibration set, we can compute the non-conformity score. And therefore, we obtain a distribution of these non-conformity scores. Here is shown, for example, the distribution in terms of the empirical cumulative distribution function, but you can, if you want, also look at the distribution function. So the non-conformity scores on the data, which is real data, by the way, has a certain distribution. And you have an idea about the range of these non-conformity scores. And then for every epsilon, for every confidence degree epsilon you would like to achieve, you can check for the corresponding percentile, and you can find this non-conformity score alpha 0 such that the probability that the real data exceeds this non-conformity of alpha 0 is at most epsilon, or at most epsilon. So the probability mass here is 1 minus epsilon. The probability that a real data point has a non-conformity lower than alpha 0 is 1 minus alpha. This is what you can do. This information you can extract from the PDF, but of course also from the CDF. Doesn't actually matter. So this is the important information you can extract from this calibration data. Okay, this is basically what I said already. So then, inductive conformal prediction computes this non-conformity score alpha j for every data point in the calibration data set. And from this, then we extract this value Q hat, which is this quantile here of these non-conformity scores alpha 1 to alpha capital M. It's the M plus 1 divided by 1 minus epsilon upper floor, this is applied a ceiling function to this divided by M. So this is the empirical quantile. We extract from these non-conformity scores. And then we construct the prediction set as follows. Given a query instance xq, we include in our prediction set all the y's for which the degree of nonconformity is upper bounded by this q head. And this corresponds to this alpha 0 that I have shown on the previous slide. So we only exclude a candidate outcome y if this the probability to observe a nonconformity degree for a real data point, to observe such a high nonconformity degree is upper bounded by epsilon. So it's quite unlikely to observe such a high nonconformity score. And then this is this more formal result that you can guarantee, that you can prove in a similar way as for this inductive, transductive variant of conformal prediction, is that assuming that our data D is IID, okay, and here we take this IID assumption, we are no longer in this transductive setting, but as I said, it's even a slightly stronger assumption here, and that our query data point is sampled from the same distribution, then this estimate here is provably correct. The probability that the real outcome, YQ, the real outcome, for example, the real digit represented by our image, is an element of our prediction set, is in between 1 minus epsilon and this upper bound here, 1 minus epsilon plus 1 divided by m plus 1. It's not possible to achieve 1 minus epsilon exactly, but you see we can get as close as we want basically to this quantity by exceeding the number of calibration data points, capital M. Yeah? So we really guarantee this probability. So let us look at our example again. This example that I have introduced this morning, where we have a very simple instance space, the real number line. We have two Gaussian distributions, two class conditional Gaussian distributions, which the learner, of course, doesn't know or may not know. It's also not necessary for conformal prediction. It doesn't make any distributional assumptions here. And we generate data points now from this distribution. What could be a meaningful nonconformity function here? One example of a nonconformity function I have given, namely the negative margin. What does it mean? Remember, our learner, at least this is the example I have given this morning, our learner learns a threshold by finding the midpoint between two observed data points for which the number of mistakes on the training data is the lowest. This is how our learner learns the threshold. And this is the threshold here, this is the T. Now we define the nonconformity of such an example xy, hypothetical example xy, as T minus x if the y is positive, we put the positive class here, and as x minus t if the class is negative. It means that if the x is on the right side, so it's on the left of the threshold for a negative one, and on the right of the threshold for the positive one, the nonconformity is negative, so it's conforming. It's not non-conforming, it's conforming. But if it's on the wrong side, then it's non-conforming, and the degree of non-conformity is just the distance to the threshold, which is certainly a meaningful notion of non-conformity. Yeah. Okay. So, and if we do it in that way, then you can apply conformal prediction, or in its inductive variant in this case, in principle, of course, also in the transductive variant. directly. I mean, you don't need anything more. I did this with a simple example. So I generated some training data according to this distributional assumption we make, which the learner, of course, doesn't know. Some positive examples, some negative examples. And on this data, the learner produces a threshold of 171.77. This is the model, so to say, it learns. And then we can, using this model, we can compute or approximate the distribution of nonconformity scores by applying our nonconformity measure on calibration data. So I generated, in this case, a lot of calibration data because I could do it. It's just synthetic data. And you come up with this cumulative distribution function of the nonconformity score, And you see, for example, that it's very unlikely, for instance, to exceed nonconformity of 10, for example, or the other way around. The probability that a real data point has a nonconformity smaller than 10 is very high. Yeah? And more specifically, you can extract the 90th percentile, if you want, from this cumulative distribution function, which is 8.85. So it means that the probability that a real data point has a nonconformity degree of smaller or equal 8.85 is 0.9, is 90%. So therefore, for epsilon equal 0.1, what conformal prediction delivers as a prediction is what? Is only the negative class as a prediction region if our query instance is smaller than 172.92. Only the positive class if the query comes from, has a value of 180.62 or even higher. And in between, it delivers a non-informative prediction if you want. It says it's positive, negative, I cannot say. And this is, of course, a meaningful prediction. So how do these values here, how are they derived? It's just this threshold, this 162 point something, plus minus this 8.85. Yeah? And this is, of course, a meaningful prediction. It means that in the middle, somehow, the learner cannot decide exactly where is the boundary between positive and negative. We know that both classes are overlapping in the middle. And more to the boundaries, more to the extremes, it makes a decision. So it's certain enough that it's either negative or positive because it can reject this null hypothesis that the class is negative, for example, if it's very much on the right, or negative if it's very much on the left. Okay, so this, of course, makes perfect sense. And this is a kind of confidence interval that you probably would also have expected from classical statistics. Here it's derived in a slightly different way and without any strong statistical or distributional assumptions. So just to conclude, a few remarks on conformal prediction, which, of course, again, I could not discuss here in too much detail, but I hope you understood at least the basic idea. This validity property that I introduced here is also called marginal coverage. The randomization here is over this entire data generating process and the prediction procedure, which means that this coverage of 1 minus epsilon is neither guaranteed for a given concrete sequence of data points you have observed so far, and it's also not conditioned on the query instance XQ. So it's not per instance, so to say. It's not that you can say, given this sequence of data that I have seen, and given this new query instance XQ, the probability that the outcome is in my prediction region is 1 minus epsilon. This is not what conformal prediction guarantees. It guarantees, in a sense, a weaker property. If you generate data and apply conformal prediction in this way, the probability that you make a mistake, produce an invalid prediction region at the n plus first position is 1 minus epsilon, or on average, the probability to make a mistake is at most epsilon. Yeah, so it's in this sense a bit weaker guarantee, but there are also works on extending conformal prediction toward conditional coverage, so that you can make more valid statements conditioned on the new query instance that you have seen. And even very recent work on controlling even more general notions of risk, not just validity in the sense of coverage, but also even more general notions of risk regarding your prediction sets. Still, conformal prediction does have, I think, a number of nice properties. So it's completely agnostic to your underlying model. You can apply conformal prediction, so to say, to conformalize every learning method that you can think of. Basically, by applying conformal prediction to the predictions delivered by the learning method, you can conformalize it in the sense of producing predictions coming with a certain guarantee. It's also agnostic to the underlying data distribution, so it doesn't make strong distributional assumptions. It's distribution free in a sense, and it's valid also for the finite sample case, so not only asymptotically. It's not only asymptotically, but also for the finite sample case, which is again a desirable property, something that you would often like to have in practice, where data sets are, of course, always of finite size, never of infinite size. Okay, so, this is a perfect timing, except that I don't have time now for questions, but we had some in between, and I guess there will be a couple of minutes more if you have more questions on this part. Otherwise, I would like to stop here with this part of my tutorial, and then continue tomorrow with the last part about epistemic uncertainty. But yes, there is another question.
Yeah, thanks for the lecture. So to the extent I understood, I feel like lots of these ideas from the conformal prediction kind of is incorporated into the Bayesian formulation. For instance, the online setup also, like the equivalent to my view, seems to be like this iterative Bayes rule update, or like this non-conformity score kind of, it seems like the likelihood function there in the Bayes rule basically is kind of similar in some ways to the non-conformity score. So I was wondering, like, is there any relevance, or am I missing something? So is Bayesian formulation some kind of in some way kind of universal formulation that also is compatible with this conformal prediction?
Again, I have to say that I have some trouble to understand this acoustically. I'm sorry, but I didn't fully understand your question. Could you maybe speak a bit louder?
Low voice, like
yeah, maybe you try a bit louder, but I have also the feeling it's the microphone. Okay. Can you maybe?
I can try
a bit louder.
Keeping it a little bit closer to my mouth.
Yeah.
So I was wondering if Bayesian formulation.
Bayesian formulation?
Yeah, in which we have like a model that learns in a Bayesian format, has any similarity to this, or is it compatible with the conformal prediction? Because as far as I understood, for example, the likelihood function in the Bayesian update could be seen as non-conformity score. And even we have like this kind of, so two kind of a stage of non-conformity integrated into the Bayes rule in a sense, because we have this parameter posterior of the parameter that is also kind of conforms to the data based on the likelihood of the parameters given the data.
Yeah, it's a good question. Yeah, it's a good question. And yes, you are perfectly right. Nothing prevents you, in a sense, from combining the things. So, for example, as I said, one way of defining nonconformity score is to learn a probabilistic predictor and then define nonconformity in terms of 1 minus predicted probability for the outcome you look at. And this probabilistic predictor might be learned in the Bayesian way, if you want. So nobody prevents you from doing that. Other than that, I mean, the two approaches are really, as I said in the beginning, developed in a quite different spirit and in a sense even orthogonal to each other if you look at it from the point of view of, let's say, statistical schools of thought. The Bayesian machine learning is rooted in the Bayesian way of thinking about statistics, so Bayesian statistics, whereas conformal prediction is really rooted in classical frequentist statistics and based on hypothesis testing, counting frequencies and so on. And also the type of guarantee that is given here is more the classical type of guarantee you find in frequentist statistics. If you repeat the process over and over again, then you have a certain guarantee of validity and so on. And this is quite orthogonal also to the type of guarantee that is given in the two methods. For example, in Bayesian inference, you typically have this per instance guarantee. What you do when you do model averaging and prediction and so on is you condition everything on your current query data point and also on the data you have seen so far. So everything is conditional to the data you have seen so far. So in terms of the spirit and basic ideas, these two approaches are rooted in different statistical paradigms, but still you can combine them if you want. If you are not a purist, either Bayesian or frequentist, then nobody, and a bit more pragmatic, go ahead and you can do for sure. Yeah, but still they differ a lot philosophically and also mathematically.